Good evening, and today is the last live session for this course of Computational Fluid Dynamics. So we are towards the like end of this course, and we have discussed a lot of things and how to like solve various differential equations, mostly uh, equations which are related to fluid dynamics and transport phenomena in general. And we have discussed a lot of techniques and a lot of properties that we have, and we have mostly focused on finite volume based methods. And so today I'll try to like recap some of what we have done, and like try to highlight few important areas that we have discussed so far, and also like if you have something to discuss, we can discuss about that. So, like mostly what we have to cover, we have already covered, and this is kind of like a recapitulation of what we have done so far. So, if anyone wants something specific to be like discussed, you can like uh, say if there is anything that you want to discuss. So, we have mostly focused on uh, solving a transport phenomena equation. So, like in the beginning of the course, we had like discussed what are the like different types of equation, and we had also like said that we want to solve an equation of this form. So by now you must be familiar with this equation form and what the different like terms signify. So this term is a temporal term or the time dependent term basically. This is the convective term or the advective term if you want to be very specific, then you can say it is the advective term. So, or you may combine these two and in the left hand side, and together they can be the, you can call it the inertial term. So this is basically a transport equation. This whole thing is a transport equation, and uh, like uh, so this is a general transport equation. And this equation is uh, in an Eulerian framework. You may be familiar with that. As opposed to a Lagrangian framework where you follow a particular particle, this particular equation is like you are observing a space, and whatever the formula, the phenomena is happening there, you are modeling that in form of these equations, and that will like give you this form of a transport equation. So in this transport equation, if you combine these two terms, this is basically the inertial term. So for example, if you are writing Newton's second law, then like the ma part, the mass into acceleration part, denotes the this left hand side, and any other transport phenomena that instead of momentum, if you are doing mass conservation or some species conservation or energy conservation, the properties that you associate with inertia, like resistance for change, so that that those properties can be attributed to the terms in the left hand side. What about the right hand side? Right hand side we have two terms. This first term is the diffusive. So in this diffusive term, we have this diffusion coefficient. Uh, and earlier. So in the left hand side, we also can mention that this rho is the inertial coefficient or the density, if you know. So this may be thermal density if your phi is temperature, or this may be regular mass density if your phi is v. If phi is v, you get the Navier-Stokes equation. There you also have a pressure term that is not mentioned in this general transport equation. So phi here can be, let's say, temperature. So this rho may be the rho Cp that we usually use. Hmm. In the advective term, you can see a velocity is added here. So if you are solving a Navier-Stokes, obviously this velocity becomes an unknown. However, if you are solving for some other parameter, some concentration or temperature, then this V can be a known parameter that you have obtained from Navier-Stokes. Or also you can couple this with the Navier-Stokes equation and have a coupled set of equations where you also have a species transport which is influencing your fluid flow, and the your fluid flow is in turn influencing your advection term. So it can happen, like for example, here you can see how the velocity will influence the species flow. And in the Navier-Stokes equation, you might have a body force term which involves this phi, and thus influence the fluid flow, the velocity. So there can be a coupling that takes place. So, and other than that, you have this source term. So if you are solving Navier-Stokes, the source term will include the gradient of pressure. So minus grad P will include. If you are solving for some heat equation, then it might include some thermal energy source. So these are the different terms of this equation, and we have seen how to solve these equations one by one. First of all, we have also done one thing that we have done very long ago, so you might have uh, forgotten. That is the elliptic, hyperbolic, and parabolic classifications. So elliptic, hyperbolic, and parabolic classifications of differential equations. And there we had not really want to classify this whole transport equation. So there what we have mainly done is taken some simplified equations and tried to classify that. And what is our basis of classification? Our basis of classification was how the information is being transported. So that's what we were really interested in. So if you take an if you take an equation, let's say second order differential equation. So we had taken second order differential equation because this is the second order from the diffusion. The diffusion term is second order. So we had taken a second order differential equation. However, we have also generalized for a first order equation. Also, we can find out elliptic, hyperbolic, or parabolic. There we have to convert it into a second order term and compare. We have done some problems related to that. If you go back to the assignments of those first few assignments, there you will find the problems relating to that as well. Please have a look into that. So the main agenda is to find out how the information is being placed. If you have an equation like this, so here x and y, these are the two independent variables. We might also have x and t, that doesn't matter. So it is basically two independent variables and a second order differential equation. So this is an example that we had taken uh, uh, for establishing what elliptic, hyperbolic and parabolic will look like. And we had found that for elliptic case, we must have b square minus 4ac. This should be less than 0. This is elliptic. What happened in these cases? What happened in these cases? So if we had a elliptic equation like this, then our information would travel across the x and y directions at infinite speed. So here, uh, the property that we have is information travels at infinite speed across the domain. There were no boundaries where information couldn't be transported. One example of the elliptic equation was the Laplace equation. So Laplace equation, how would you get Laplace equation in this general transport equation? So in the general transport equation, if you take only the diffusive term and equate all of the other terms to zero, then you will have a your equation will be simply grad square phi is equal to 0, provided gamma does not vary. So this is a Laplace equation. This is called the Laplace equation, and this is elliptic in nature. It is such that like if your phi increases at any boundary, the information will be traveled across the domain. What other equations are there? Yeah, so if your suppose b square minus 4ac this is equal to 0, then we will have parabola. So here comes the concept of characteristics. So this has one real characteristic. In elliptic, there are no real characteristics, zero real characteristics. So one real characteristic. So here, basically, what happens is uh, information travels only to points at one side of the characteristic. So what happens here is your characteristic divides the characteristic is basically a curve in the domain. So it divides the domain into two parts. In these two parts, one side will have the information, the other side will not have the information. So where does this come from? So these come from let's say you have only the temporal term and the diffusion. So if you have the temporal term and the diffusion term, what happens is you will have some initial conditions with time. So at initial condition, let's say t is equal to 0, there is a spike in this concentration phi at some point. So that concentration spike will be felt at t greater than 0. So after t equal to 0, all the other points where the time is positive will know that such a spike has taken place. And before t equal to 0, this information will not be there. So t equal to 0 is such a line which we will call as characteristic, which has divided the domain into two parts such that the information is not carried across the characteristic. So it stays at only one side of the characteristic. So that is what defines a parabolic. A parabolic. equation. So if you have a temporal term and diffusion term only, no advection or source term is there, that equation will be parabolic in time. So in time, it will be a parabolic equation. What is the other equation? P square minus 4ac if it is greater than 0. So this is a hyperbolic. So hyperbolic equation you will see in case of waves or something where a velocity is important. Hmm. So hyperbolic equation is basically where information travels at finite speed. So here there are two real characteristics. Two real characteristics. So to be fair, if you think about hyperbolic in the way you think about parabolic equation, here you will have these two characteristic curves, and this two characteristic curve will actually divide your domain into four parts. And similar to the this parabolic case, here also you will see that your whatever information you have is confined to one of these parts, and this gives you an illusion that actually not an illusion. This creates an effect that the information is traveling only at a finite speed. So that's why we say this information travels at a finite speed. This actually comes from the fact that it has two characteristics. So, so these are the three equations, three ways we had divided our this differential equation. Okay, so let us again come back to our general equation. So, what we let me number this. This is the first one. This is the second one. This is the third one. This is the fourth one. So we had started next exploring different methods of solution. So first we had seen if there is three and four, third and fourth term, first and second is not there. So that is a very common condition that we have. Like even in fluid flow, when Reynolds number is very small, you will only have like grad P and the viscosity term. So that falls under this category. So mm, that is called like the Stokes flow regime. Other than that, what we had discussed mainly is basically conduction equation. So in steady state conduction, you will have only these third and fourth terms. So when you say steady state, that means time derivative is not there, so term one will be not there. And when you say conduction, you would mean that no advection is there. So the second term will also be. So steady state conduction equation will contain only 3 and 4. And we had for our simplification, we had discussed the 1D form. What is the 1D form? This is the 1D form. So this is very evident that this is just the 3 and 4 term. So a simplified version of the general equation. So we had discussed what are the methods that we can take to solve this. So for that, one concept that we had come across is D form, V form, and M form. So what is this D form? D form is simply differential. So differential form is the way we write the equation. So this is D form. What is V form? V form is variational. So variational form, if you recall, it is basically a form where you write this in terms of in this way, basically, where V is a variational parameter and T is the temperature itself. What is A and what is L? A is a bilinear operator and L is a linear operator. So how we arrive at this equation? We basically take integral over the domain and like using a variational parameter, and we use this variational parameter and using by parts we boil it down to this particular equation. So for this equation, what will be the V form? So for this equation, the V form will be, let's say 0 to L is the domain. So it can be something else as well. So 0 to L is the domain, then this is K dt dx. Hmm. dv dx is equal to integration 0 to L s d dx. Plus there are some boundary terms. So if you recall these boundary terms, like boundary conditions can be of two types here. One are the natural boundary conditions and another is essential boundary condition. So I suggest you go through this derivation so that you like will have a good feel of what is being talked about. So, what are the natural boundary conditions? So, natural boundary conditions are basically which you will implement using your variational parameter. Hmm. And essential boundary conditions, essential boundary conditions, basically you can put the values there. When you do by parts, there are two terms, right? Uh, One term has no integral; it's basically values are the boundaries. So there you can put these boundary conditions, and by putting those boundary conditions, you will have this get this boundary terms. So natural boundary conditions are naturally implemented using the variational parameters, and essential boundary conditions are the values that you put in place of t. So you might have t at 0, t at L. So uh, those will be essential boundary conditions. So in this particular case, t is essential and dtds will be natural. Hmm. But that will change from case to case. Hmm. But this is not like the rule. So the rule is which is implemented through V is natural boundary condition, which is implemented to T and its derivatives is essential boundary conditions. Hmm. Okay. So yes, so this is the V form. Hmm. I suggest you do this like V form to V form derivation yourself. And there is also another M form. So M form is nothing but like yeah, it states that the statement of it is goes like this: if you have a G epsilon, which is also this depends on this A and L. So here you can see that this is A and this S, this right hand side, this whole thing. including the boundary term will fall under L. Let's just say it's P plus epsilon P plus epsilon P. So if this expression is there, it says that the minima of this expression comes when epsilon is equal to 0. So that means whatever the minima is there will come at epsilon is equal to 0. So this is the info. It's a like not an equation per se, directly in the form of an equation, but also like this can be an way to look at it. And we have later seen some methods which uses this kind of a concept in form of like gradient descent methods. Uh, so steepest descent or conjugate gradient descent. So those use this kind of a ideology where you have to minimize certain expressions. Okay. So here we have discussed the diffusion term and the source term, and we continue to do that. So, these are basically the different forms. So now we try to solve them. Uh, so we try to solve them. So I'm simply writing this. Keep in mind these are the third and the fourth term of the general equation. So what are the methods that we use? One are the weighted residual methods. So the weighted residual methods. So what are the weighted residual methods? So weighted residual uses a concept that, like, let's say your equation is some whatever your equation is. This is the equation that we have written down here, and this we write it, let's say, in the form such that this L of t is equal to 0, where L is basically this operator. Hmm. So we have converted this into an operator. So now we say that we find an T approximate solution. T approx. So whatever your L T approx will be, this will be different from your LT, right? The actual solution. So this we have named as R, which is the residual. Now this residual is minimized over a domain. So weighted residual method is simply uh, we take this residual and we integrate it over the whole domain. Let's say omega is the domain. So this is a very symbolic notation that I am using. And we take a weight W in this. And this should be equal to 0. So what we are doing, instead of solving the equation as it is, that might be difficult to do. What we are actually doing here is finding out an approximate solution in such a way that the residual is very close to 0. So the overall residual is very close to 0, and that we are doing with the help of a weighting function W. So instead of getting an exact solution, we are getting an approximate solution. So and like that is actually, like, you can say, the beginning of the CFD philosophy, where we like give up solving exact solutions, but try to find approximate solutions with less effort. So so residual methods, weighted residual methods. there are a lot of type of weighted residual methods that we had done. So the important ones are like if your W is simply del R del some parameter k. Let's so this is basically simply like saying that this is a least square method. This is least square method. So you choose a approximate solution in this case with some parameter a. You can have multiple such parameters like ai. Hmm. So you choose a lot of parameters and then you simply have a r square d omega integration with omega and you put their derivative equal to zero. So this is simply minimization uh, like minimization of the square. So this is least square method, and you can choose a lot of parameters AI, and for each parameter you get an equation which will be much simpler than the differential equation you are aiming to solve, and you can solve those equations and get the parameter values. So you can find the AI and put that AI in your approximate solution, and you will get the approximate solution that you are looking for. So this is a least square method. What else is there? There is another called point collocation. So in point collocation, we have a delta function. So here also we have some parameters. What are the parameters here? Xi is the parameter. This is point. So point collocation says nothing but that at these xi points you must have the correct value. So it is tries to get the correct values at certain important points, and that's how you get the approximate solution. So there are other methods as well. One is the spectral method. So spectral method is basically like W you choose as a infinite series, some infinite series. So infinite series it may be Taylor series or like mm, some uh, Fourier series. So these are the spectral methods. So another method is this is the important one is the Galerkin method. So Galerkin method we have W as uh, the approximate the approximate solution that we have. So y approximate or t approximate as we had like previously. So this is a gelatin method, and how why this will become important because we will use the same concept in your finite element. Hmm. So I am just discussing these things. Like if you have anything specific to discuss, we can discuss that as well. Okay. This is like a final discussion class. So if you have any like specific thing to discuss, we can focus on that. Right. So, if not, I will move to like the other topics that we have discussed and like try to cover as much so that you have like every topic in one place where so that you have a good reference point from where you can prepare. So now, after this, we move to domain discretized methods. So till now, whatever the method we were saying about the weighted residual methods and the other direct methods, so they try to solve the whole solution in the whole domain at once. So all the approximate solutions that we were talking about, that were like a whole domain solution. Now we can also do one thing. We can divide the domain into small discretized parts and solve those individual parts and then stitch them up together. Hmm. So let's say we have some domain like this. Hmm. So what we will do is basically in the next step, we discretize this domain into, let's say, small pieces. We can use different techniques to discretize. So we can discretize this domain into small pieces, and let's say these and let's say each of these domains are solved individually using the methods that we had discussed or some other methods, and then they are stitched back together. So this is called like, meshing, or discretization, if you will. Yeah. So if you divide this and then solve for each small element or domain or whatever you may say. Hmm. Control volume if you are doing finite volume method. Hmm. So it's small element slash control volume. Then uh, prepare a global uh, set of equations from here, and then solve, and then mm, like uh, find the global approximate solution from, or whatever you are looking for basically. So uh, here if we divide into small volumes, so in, let's say, at first we had discussed FEM. Let's do FEM. So FEM we had discretized into the small domains, and then we use Galerkin method. So this is the discretized Galerkin process. So we use Galerkin methods, and then we reduce it to set of linear equations. Hmm. So in forms like, if you recall, in forms such as NiTi plus NJT. Hmm. So after assembling all such equation, you get some A T is equal to B, or like KTF, whatever you may write it as. So this P and B, they are column vectors, and A is a matrix. And then we try to find out A inverse P. So this is what is the story of FEM, of also the other methods. What are the other methods that we had discussed? Uh, what are the other methods that we had discussed? We had discussed FDM, finite difference method. So FDM is basically we take Taylor series expansions. So we take Taylor series expansions till a certain point. So uh, we truncate at a certain point. So expansions and truncate at required accuracy. Hmm. So uh, we write the derivatives in terms of algebraic combinations of uh, pi pi plus 1. So these are the grid point values: ti minus 1, ti plus 2, ti minus 2, whatever is required basically, and so on. So however points are required, and depending on from the Taylor series expansions, we derive the values of the derivatives as algebraic expressions. Then we write it in all of this in terms of a matrix like this 80, and we solve that. So this is basically for FDM. So here in FDM, you see there is no element or like grid points. So elements or nodes. Here we have grid points. So these are grid points, and these are only important here. These points are the only things of importance. So FDM finite difference method also struggles if there is complex geometry, because then the like arranging these grids become very difficult. In this finite element method, what happens? You divided the domain into different elements. But these are the nodes, and this whole space is the element. And both of these concepts are very important here. Element and nodes, they are very important here, because you have these like interpolating functions, like shape functions that you use to find the values which are not at the nodes. Whereas here you do not really do anything such that like that. You can definitely interpolate between the grid points to find other values, but here what are important here are only the grid points in finite difference methods. So a finite difference method is definitely much more primitive than a finite element method, which is more like mathematically robust, because it like goes through a minimization process of like Galerkin's method. It like goes through. all the variational formulations. So next that we had discussed is finite volume. So till now, to just to remind you, this of this major governing equation, we are discussing only this three and four. However, you can definitely include one and two also in all of these methods, FEM and FD. But the examples that we have solved, if you like go back to the assignments, which I like encourage you to do, please like go through all the assignments before appearing in the exam. So there you will like in these assignments you had mainly focus on equation 3 and 4. However, you can definitely add your equation 1 also. Sorry, the term 1 and 2 also, and like such modifications then would need to take place. So what about FEM? FEM is basically like here instead of element you have control volume. So you have a control volume, and you have a grid point which is at the middle. So the grid point is at the center, and here we are like more concerned about the flux through the different walls. So here the next neighboring grid points, let's say uh, east, west. So these kind of notations are also there in the finite volume method only. South, north. And the interfaces may be interfacial points may be represented by the small letters. And we like calculate the flux through the these different interfaces, and then like from there we develop the equations. Hmm. For like calculating the derivatives, we use something called like the something like the shape function. Hmm. But we can have like for different terms we can use like different forms of the function. Uh, as per our need. So at the end of the day, like what we would want from here to emerge an equation of this. So there will be top and bottom as also if it is a three-dimensional case, or this north and south will not be there if it is a one-dimensional case. And additionally, there will be a B term, which is like a kind of like a source term. So here we have like certain like rules that we need to follow uh, so that these uh, like so that we get a physically consistent solution. So here this A, these terms, except the B, these terms are basically the fluxes. That is the influence of the neighboring temperatures to this particular temperature point. And B is kind of like a source of generative term. So this comes from the like the fourth term in our generalized transport equation. And this the other terms are generally from your like the diffusive term, and also if you have a convective term that also can be incorporated, and then also you will have this same kind of equation. What I've so this is true. So B is due to the fourth term. Uh, all these AITEIs, these are due to the third term, and also the second term, if second term is included. What about if the first term is included? First term, if it is included, then we will have a term of this kind. So AP0, P, P, where this is basically the previous time step. So AP0, P0, this is for the first term. This is the unsteady term. So this is basically like the previous time step, what has happened. The influence of that is also carried over. Mm. So, from the governing equation, we'll try to come to this particular format uh, uh, using the concept of flux conservation. So that is basically the main crux, main gist of our finite volume. One thing that must be understood is that all these AP, all AIs like AE, AW, AN, AS, and also this AP0, all must have the same sign. Why? Why is that the case? Because each influences the other. So if TE increases, it must also increase TP. It can never happen that the bound, like the neighboring point, is increasing in value, while the point itself is decreasing its value. And also, like if the previous time step value is high, then the next time step also will have that influence over it. So it can never have an opposite influence. That will be physically inconsistent. So this is a very important thing that must be like uh, mm, followed always. So always this must be ensured that they must have the same sign. Hmm. So like this is something that you must keep in mind. So as we have already like kind of discussing about this like temporal term. So temporal term also like we can discuss. Hmm. So next we also move to a heat equation. So heat equation case is basically we have this and this. So what is this? This is a heat equation. Hmm. So what is the speciality of this? This is basically nothing but a like special form of the generalized equation where the first and the third term. So the second, which is the advective term, and the fourth, the source term, these are not there at the moment. Hmm. So if we try to discretize this, if we try to discretize this, then we can we can always do that, but we can use like two kind of steps for doing this. Hmm. So let us first see the problems that might occur in the finite volume approach, because we were doing the finite volume approach just now. So in the finite volume method, what will happen is that we will have encounter this particular integral, uh, which is the integral t to t plus delta t, t. Why we will incorporate this integral in finite volume method? Because we this is how like we do in like suppose we have a equation. Let's say this equation that we had previously been solving. So if you are solving with the finite uh, volume method, then you expect that this whole equation is to be integrated over the whole control volume. So each control volume will have this integration. So if you notice, this is nothing but a weighted, like discretized weighted residual approach itself, where the weighting function is one. So here the weighting function is one, as opposed to the finite volume method where a Galerkin method is followed. So here It is not a Galerkin method, it is a weighted residual method where weighting function is simply 1. So that gives us the flux conservation forms. Hmm. So similarly, we will, if there is a time involvement as well, we have to integrate this over the particular uh, like time control volume, if you must, if you may say. So between this t and t plus delta t, we must also have an integral. So that will lead us to these kind of terms. So how we treat this term will basically determine what kind of method we are using. So this can be in general. So this can be in general written down like this: 1 minus f uh, t plus f t plus f. So what is this f doing? F is a non-dimensional parameter, as you can like see here. From you can understand if you do a dimensional analysis that this is a non-dimensional parameter. And from the format, you can also guess that its value is actually meant to be between like 0 and 1. Hmm. So that is also very clear. So, so what are the values that it can happen? It can take. So it depends on which portion we want to give more importance to. If more importance is to be given, if more importance is to be given to this previous time step over the next time step, then it should have a value as close to 0 as possible. If more importance is to be given to the next step, then it must have a value which is close to 1 as possible. So what are the extreme cases? F is equal to 0 is an extreme case. This is also known as an explicit scheme. The reason it is known as an explicit scheme uh, is because you do not really need to know the next time step value to find out any other uh, grid value. So this is actually computationally very less expensive. Computationally least expensive. So this is very simple. But what is the downside of this? This is conditionally stable. So this is not stable throughout for any value of discretizations of delta t and delta x and so on. So what is the value? What is for what it is stable? This is only stable if your alpha delta t divided by delta x square. This is less than equal to half. So this is an expression that you can remember. So this is an expression which is of big good importance. This expression of importance that you can remember. So what is this alpha delta t by delta x square called? This is also called like the discretized Fourier number. What is alpha? Alpha is nothing but the like diffusion coefficient, non-dimensionalized. So, with rho. So, if you simply put the rho this side, if it is rho Cp that you can put this side. So, alpha is basically in heat equation you will have this coefficient in the diffusive term, that is alpha. Not non-dimensional. This whole term is non-dimensional. But like alpha is like the diffusion coefficient that you will have in the heat. What is the other extreme? Other extreme is f is equal to 1. So f is equal to 1 is basically an implicit scheme. And this is much more like computationally expensive because like you will need to form a whole matrix and a matrix inversion to be performed to find out each time step. Hmm. So this is an implicit. Hmm. And but the advantage is this is unconditionally stable. So this is unconditionally stable. Another scheme is there, which is Frank Nicholson, which has a middle ground. F is zero point 0.5. So that is also there. Hmm. So other than that, you can also have finite difference method schemes. One is CTCS, which is central in time, central in space. So, if you remember, in finite difference method, we used like Fourier series to find out the time, like the space discretizations previously. So, in time discretizations also, we will do the same. Hmm. And like CTCS is basically you are doing a central time difference. In spatial, when you were doing for the spatial variables, it was seen that like the central differences generally have less error. But here there is a problem. Uh, CTCS is unconditionally unstable. So this is not stable at all. Unconditionally unstable. So CTCS we cannot use. What is conditionally stable is FTCS. So space you can use central discretization, but for time you need to have a forward time state. So this is stable only when your the Fourier number that is less than equal to half. So this Fourier number is very important in these FTCS schemes and also the explicit scheme. So from here you can have like questions which will ask you to like find out the required dimensions of the discretizations. Hmm. So now we can like after this we will discuss about the solution techniques using this like the matrices that we have like developed from all these methods and how to invert those matrices or like solve the system of linear equations. So I'm giving you a small break and we can like continue after that. And like if you have anything to discuss also, like it is like it will be very much appreciated if you can bring that up and we can discuss it. Okay. So let's again resume after like a break of a couple of minutes. let's resume. Uh, does anyone have anything to discuss in particular? Okay. So, like using all these methods, what we finally arrive at is a form like this. Ax is So whatever solution you choose, like maybe finite difference, finite element method, or finite volume method, finally you will have a set of linear equations, and these linear equations can all be arranged in a particular manner. You can also provide boundary conditions at the boundary nodes or boundary elements or boundary grid points. Hmm. So uh, from there, you may change few of those equations and also replace them with a suitable equation of their own. But in the end, it will all lead to this form: Ax is equal to b, where A will be some a11, a12, a1, 1n, a21, and so on, and an1 to ann. It will be a square matrix. Why a square matrix? Because you have n number of variables. So for n variables, x1 to xn, you will need n equations. So that will give you a square matrix of this form, and this will be equal to b1, b2, and so on to b. So these are like generally in this all the body force terms or like any such forcing terms, source terms, those will be there, and also the boundary conditions will also be like applied within these B terms. And now what we have to do is basically isolate this X matrix, this unknown matrix. So for that we need to really come to this particular. So one simple way is basically like Gauss elimination. So Gauss elimination is is something that we all do when like a simple let's say two linear equations are given. Then what we try to do is basically eliminate. Uh, we uh, we try to eliminate one variable using the two equations, and then uh, we get one variable, one equation, and then we'll try to solve. So this is basically Gauss elimination. So Gauss elimination, here we try to make all these variables zero, such that like we target one equation, let's say the last equation, we will try to make all this a n minus 1 to a n n minus 1 to a n1 to a n n minus 1 all 0, such that it will only be some different a dash n n xn equal to some other b dash n. So this will definitely change, and you will get the value of xn and substitute back in the n minus 1 equation, and then get its value, and so on and so on. So that's the Gauss elimination method. So, like for application of this kind of methods, one concept is very essential that you must have is rank nullity. So, using this theorem, basically you will try to guess whether this equation has a unique solution or not. So, there might be equation set of linear equations which are not consistent, and they might either have like infinitely many solutions or have no solution at all. So it is very important to note like whether this is possible or not. For that, we need to find the rank of a matrix. So if our rank of A is equal to rank of A augmented B. So this is basically a matrix which looks like this. So A augment B. This looks like, so this A11 to A1n nn. So all these elements are there, and the last column is simply B1 to Bn. So basically, this B column is augmented to the A matrix. So that's why this is B augment A. So rank A equal to rank A augment B is equal to n. Then unique solution exists. If this is not equal to n, then but these are equal, then infinite number of solutions exist. So unique solutions does not exist. Infinite number of solutions will exist. So, like these cases may arise if the boundary conditions are improper, and that may like lead to infinite number of solutions. So, another case might be if these two are itself unequal. Hmm. So, then this is there is no question of this, and this is basically no solution. So if such a case arises, it means there has been some like mistake in the formulation, and the formulation procedure has not been correct, and thus we are getting a case where there is it exists no solution. So we'll have to troubleshoot to find out the problem if such a case arises. And infinite solutions will generally refer to like any error in application of boundary conditions, such that like the variable can have multiple solutions, infinite number of solutions. So these are the three possible cases that may arise from our rank nullity theorem. And it, other than these elimination type methods, we also have iterative methods. So what are these iterative methods? Uh, so iterative methods can be of many types. So like uh, two popular ones are Jacobi and Gaussian. Like these are very common to you. I would assume so. So in Jacobi method is basically we what is Jacobi method? Jacobi method, like we first assume some x. So this is like an approximate solution that we are assuming, and after that, x0 that we are assuming, and then we like first of all will have to decompose for both these methods. We will have to like decompose our A matrix into a lower triangular matrix, a diagonal matrix, and an upper triangular matrix. So you can so this D contains all the diagonal terms, L contains all terms which is below the diagonal, and U contains all the terms above the diagonal. And also it must be chosen in such a way that this is diagonally dominant. That means the largest coefficients are almost always present in the diagonal. So, in such cases, the solution, like the convergence of the solution, is also ensured, and like the errors are minimized. Especially for these iterative methods, where like for certain iterations, for certain guesses, the coefficients, the next iterations might blow up to very large values, and thus the solutions may not converge. So we have to ensure that the D, uh, uh, the diagonal, contains all the larger coefficients. It must be rearranged in such a way. If you like see the example problems that we had like done in this portion also, you will like understand how we can like rearrange the equations to really in such a way that this is the case. Especially like if you are doing finite difference methods or like finite volume or finite element, any of these methods, you will automatically see that the equations that you are getting are diagonally dominant. And also they will also have another properties that it will be sparse. That means most of the elements will actually be zero. So only near the diagonal some elements will be there which will have non-zero values. So some of the methods also try to utilize this kind of these sparsity of these matrices. One of them is the tri-diagonal methods, or similar like methods which are only like focusing on the diagonal and the diagonals which are like offset the uh, the diagonals offset to the diagonal columns. Well, not columns, like parallel to the diagonal lines. So if some offset to the diagonals are only considered. Hmm. So that speeds up the solution processes. So tri-diagonal matrix algorithm is one such thing that has been discussed. Uh, we can look into that. So here we will assume that we start from the like the first variable and then work our way down. Hmm. So like so D is basically the coefficient for the uh, this coefficient of the x that we are trying to find. L will have the values that we have already found the coefficients, and U will have the values that we are yet to find the coefficients. So for here, we will actually have this new x1. There will be D inverse. Hmm. So D inverse will obviously be there, and uh, you start to work it. Hmm. So if I have just this dx, uh, this is equal to then b minus L plus u x, right? So this is basically taken as a new step, and this is as the old step. Hmm. So here I have this x1, which is the next interval, which is basically like d inverse b minus d inverse L plus u x. So from here you have a new guess value of x. So then you can iterate. So this is Jacobian. What about Gauss-Seidel? So in case of Gauss-Seidel, what generally happens is the values that we have already got, let's say, which are present in the lower diagonal matrices, are also included here. So here will also assume an x0, but in this case, the x1 will be not d but L plus d inverse d minus L plus d inverse u x. So this is basically done in a loop. So we actually do not really have to find an inverse of the like these matrices, we can go row by row, and within that loop only we will get these values. So in reality, Gauss Seidel is much faster in computational time, as well as like convergence is also much faster. Hmm. So uh, you should also try to like remember like the maximum number of iterations that are required for getting a accurate Gauss-Seidel solution, which is k, which is the number of iterations that should be greater than your m divided by log n 1 by root. So m is accuracy. So m is accuracy. If it is like 8 decimal accuracy, then m is 8. If it is like 6 decimal accuracy, m is 6, and so on. What is rho? Rho is spectral radius. So rho is spectral radius. So how to find spectral radius? Spectral radius you can find from the this A matrix. Hmm. So A matrix you can find the spectral radius. So, a spectral radius is simply mostly taken as the like the norm. Hmm. So and also like this is taken if you make B a identity matrix. Hmm. So you first make to find that spectral radius first you make D as identity matrix. So you perform row operations such that D becomes identity matrix, and then second you find the norm of it. So which norm is mostly accepted here? You can find the infinity. So you can find the infinity norm. That will give you the like mm, best result. So again, recapitulating on what is the infinity norm. So infinity norm is basically the highest row sum. Row sum also you have to take absolute value of each element, that you must remember. So you have to take absolute value of each element. I'm not writing it down, please remember. And what is the first norm? First norm is highest column sum. Again here also you have to take highest the absolute value of each element, absolute value of each element and sum it up. So these are the like two most important norms for matrices. Like for a vector, you can also remember the norm for a vector, like px norm in general. That is xi summation 1 by. So this is px norm of a vector x. Hmm. For a for a matrix, actually, like the norm definition can vary based on the which definition you are using. So the most important norm definitions for a matrix norm is uh, basically the first and the infinity norms. So other than that, you have the uh, descent, the gradient descent methods. So these are also iterative methods. So here you are basically like the idea is you try to like means if for a two-dimensional case try to assume it to be a contour. So you try define a function f which is like half minus bx. Plus C you can also say. So, oh sorry, I think I missed this. This is definitely A will not. It is like quadratic in X. So plus C also you can say. So this you have to minimize. So this is a minimization problem. So this is like kind of like an M form. So you are trying to solve that. So so here basically the idea is one idea is basically you follow grad f. This is the steepest descent, and another idea is basically grad f is like very random, so you try to like have a guess where your solution might be from the curvatures and like uh, go and offset from at the steepest descent, which is called the conjugate descent. So those are the two important ones. And it's very important that you know the algorithm. So in case of steepest descent, what you have is you first guess an x0, and then you define r0, which is the residual ax0 by b, and then define the gradient. So with calculations, you will see the gradient is actually r0t, r0, r0t, a r0. Try to remember this expression. This will be very helpful for you. Especially like if you are working on this, then definitely you will have to remember this. So this is x0 plus alpha r0 alpha. So this is basically your second iteration. Then you can simply iterate after this till your residual uh, falls below a certain value. You have to iterate. Similarly, there is a for conjugate gradient descent. There is an algorithm. There are also other like methods which are much more sophisticated than these two. Uh, they all like you utilize the similar theme of like going downhill towards a like minima point. So uh, the the algorithms are slightly different. So here also you will first guess x0, and also you will have r0, which is defined as ax0 minus. So this up to this is the same, and after that you will have p0, which at the first step you will take it as same as r0, and then you again define this alpha 0. So this is r r0t transpose p0 divided by p0 transpose a p0. So if you actually remember this, like remember the conjugate gradient descent method, so uh, uh, then only you will also remember the steepest descent. Because this P0 concept is not there. So in what is the next step? Next step is basically you find out this x1. So the x1 will be x0 plus alpha 0 p0. But also you will have to find out the next p0 in this case. So how you will do that? You will first find out the next r1. So r1 will be again uh, your ax1 minus b, or you can also like use this r0 minus alpha. 0 A P 0. Both are the same thing. Then you take beta 0, which is equal to R1 transpose R1 divided by R0 transpose R0. Yeah, P0. This is P0. And from here you will find out P1. So P1 is R1 plus beta 0. So then after that you will again go back to this step number 4 and calculate till your residual, which is R1 in this case, falls below a certain. So you are able to access the slides, right? That I am uploading. I hope you are able to access the slides. Is that available to you?
Sir, videos are accessible, but slides no.
Slides are not accessible. Um, okay, I will then like I have been uploading it to a Google Drive. I thought it was accessible to you. If it is not, then I will like put in the like video description of the YouTube. That way you can access it. All right. So I don't think I will be able to cover the whole thing. I will try like uh, mm, the best. After this, actually, like is we have discussed very recently. What are the like other topics? I will like briefly mention the topics so that like you means have that in mind and you can look at it on your own. And so after this, what we have done, like so far, we have like discussed how to. So let me first write down our main equation, which is the main transport equation. Yes. So this is our main transport equation, and we have discussed in detail this term and this term in very much detail. This also has been discussed in detail, like using our like FTCS schemes and also the implicit, explicit principles and etc. We have not really discussed much about this term, but also like means some convection diffusion like solutions. Mhm. Like discretization can also be done in a similar fashion to our diffusion term. So next we actually delve into this term. We first take this and the diffusion term. So these are the convection diffusion equations. Convection diffusion formulations are also like a generalized convection diffusion formulation may also be written. And this is mostly discussed in terms of finite volume. So, like there you will have this kind of a formulation where you discuss about JE some at the interface. You will have this. So this is basically discussing like this is I plus 1, and there is an interface E, Hmm. And how much flux is going across this tube. So there is will be some flux which is going across due to your like it's convection, and there will be some flux which is going across due to the diffusion. Hmm. And what you will basically do is uh, integrate over the whole domain these like control volumes, and then try to match these fluxes. Hmm. So if there are two interfaces, suppose for a particular uh, P, there are two interfaces. It's a 1D problem, and E and W are the interfaces, and there is no source term. Then you will actually have JE will be equal to J. If there is source term, then you will have some addition, which is source term will come from here. So, or some boundary conditions, etc., may also arise. So, this is basically convection diffusion formulation, uh, and you will have some P uh, f- formulations here as well. I think we had discussed this very kind of recently in our uh, I think week 11 we had been discussing this mainly. Uh, so they are like if you see those slides and also the like the video, you will get a good idea about how this is coming. So
The slides are visible, sir.
the slides are visible. Okay. Good to know. So, so so there you can find out. So basically uh, this difference JW minus this JE can be basically written as P phi E. Hmm. So this can be basically written as P phi E, where this phi is at the interface, and that again in turn can be written as a difference between these two like nodes, and average between these two nodes, or yeah, there can be a weightage given to one of the nodes as per the problem demands. So you can look at that. Mm. So this is basically convection diffusion formulation. And next, only one thing remains, that is our pressure term, or the general Navier-Stokes equation. If I write it in terms of the Navier-Stokes equation, then this whole thing becomes like this. So, so and plus all those other terms might also be. So here, the only thing that we have left to discuss is how to handle this pressure curve, because the rest we can handle as we have done for the general transport equation. So this pressure term is especially challenging because this is an unknown variable. Pressure is an unknown variable that we have not solved, and also we do not have any governing equation for this. We only have a continuity equation, which where also where pressure is not there at all. So how to deal with this problem? So one possible way for 2D case, we use stream function participation. So stream function vorticity method is basically we take curl of the whole equation, and that rids us of the pressure curve. So that gives us a transport equation of vorticity. Hmm. So this gives us a transport equation of vorticity that we can solve, and from there we can also find the stream function. We can use Uh, so we have two equations. One is transport equation of vorticity, and another we have a Poisson equation, which is basically grad square psi is equal to minus. So this Poisson equation. So these are the two equations that we can solve in an iterative process to find out the solution. And then we can use a pressure Poisson equation to like find out the pressure Poisson equation to find out the pressure. Okay, what are the other methods? On another method that we had discussed is simple. So it has a like full form semi-implicit method for solving pressure linked equations. So simple is the common term that we use. So simple we solve these equations directly. So what does simple do? Simple we have a guess value of pressure, and using this guess value of pressure we solve the transport equation, and then use that like solution uh, in our continuity equation. From there we find out a pressure correction equation. So pressure correction equation gives us a corrected velocity, and we have a corrected pressure, and then we iterate. So we start with guess value of pressure here, and another formulation that we have is a simpler, which is simply a revised simple. So here we guess the value of velocity. So these two algorithms are pretty much similar. We also here also we have a pressure correction equation from where we like find out corrected velocity and pressure, and but here we carry forward the corrected velocities uh, and again iterate. So here guess values of velocity, and here the guess value is of pressure. Okay, so this pretty much covers that what we have discussed so far. So you can go through all of this, and like and you must go through all the assignments that you have done. That should be good enough like for your assessment test. And also like these whatever you have learned in this course, if you are like planning to do some CFD work in whatever studies that you are doing, or whatever work that you will do in the future, it is best to like keep a concise documentation of what you have learned here, like especially towards the like the solution techniques that has been like taught here, some basics of FEM, FDN, VM, some basics of the simple method or simpler methods, and also some basics of the matrix solutions, especially the like uh, steepest descent, conjugate descent. So these documentations can be helpful even like in the. I hope it will be beneficial to you beyond the course also, so that you can look it up and uh, make use of it. Okay. So that is the like end of this session. If you have anything to like say, or any last questions, you can please tell me. Okay. So shall I end this session?
Yes, sir.
Okay. Thank you. Thanks for joining. All the
Thank you,
Thank you,
sir.
best.
sir.
Yeah. All the best.